So far we've established, I think, a few facts that almost all of us can agree on. So one is that I'd say feedback is a good thing, right? Feedback is good. At least in the context of controls, for us, feedback is going to be a good thing. Um, Thanks to feedback, we can do great things and just being more robust to external disturbances. We can take unstable systems and make them stable. We can get a system to have the type of overshoot and settling time that we want, all that good stuff. So it would not be possible without feedback. So feedback is a good thing. And then the other observation is that probably the most important factor in determining system behavior are the closed loop poles. So where those closed loop poles are going to determine stability, they're going to determine performance. So let's say pole location. Let's say in a closed loop system, the location in a closed loop system is the most important factor. Most important factor, I'll say, for system behavior. So yeah, so feedback's a good thing, and then pole location, it's got its complications too. We know it's got its difficulties, but we also know then that pole location and closed loop system most important factor. So this means that the system behavior. So is it going to be stable? Is it going to be fast? Is it going to be accurate? All that stuff. So this invites the question: can we design a controller? Can we design a controller let's say so that we can place the closed loop poles I'll say like anywhere we want. So yeah, can we design a controller so that we can play the closed loop poles? I'll say yeah, anywhere we want. Okay. So let's think about that before we dive into the math. Just this is a pretty ambitious sort of question, right? This is basically telling you, all right, or based on what we know, those closed loop poles are going to determine stability, speed, accuracy. And so, can I put some controller KFS in there such that I can put them those poles wherever I want, and therefore I would be able to determine or get the specs for speed, for settling time, for all that good stuff, just anywhere that I wanted, like at whatever level I wanted. Like it seems ambitious, but it would be great if we could, right? Like it would be fantastic if we could do that. So I'll say let's try it. Let's explore it. So let's at least try to see how this goes. And let's start with my classic um, structure right here with K and G and negative unity feedback right here, bar on the left. So of course, K is your controller. And G is your plant. So let's say controller is, we're going to call it K. And let's say this is a K of S. So it might not just be a constant. It could be a K of S that we get to decide. And in fact, let's call this NK over DK. So it's got a numerator, it's got a denominator. NK over DK, that's my controller. And then my plant, let's call that G. G of S. And this, it's also got numerator and denominator, so let's call it N over D. Oops. So there we go. Now this, the plant right here is given. So usually you have no control over what the plant looks like in most situations. This controller is what I'm going to try to select, try to design for a particular set of closed loop poles. So this is to be designed right here. So we want to find, let's say bottom line here is we need to find that NK and DK let's say to achieve the desired pole location. So you need to find NK and DK to achieve desired pole location. So tell me, folks, what do you think would be the first step right here, just to get us going in order to eventually find our NK and DK? But where would we probably start in a situation like this? Yes, I see Scott. Oh, okay, sounds good. Is that what you're going to say, Hunter? Yep. So these guys are saying, well, let's find that closed loop transfer function, and I totally agree. So how about you just take a second to do that on your own? I think with this structure, this is something that you'd be probably are pretty comfortable with by now. But let's try it. Let's try it out. So let's say first. So I think most of you know by now, like if we call the closed loop transfer function, let's say big T of S, that's going to be kg over 1 plus kg. But we can take it one step further now that we know that k is nk over dk and g is n over d. So let's plug that in and say, well, k is going to be nk over dk, g is n over d over 1 plus nk over dk n over d. So essentially you end up with n, nk, d, dk, 1 plus n, nk, d, dk. Now I'm going to do the classic thing of I'll write the 1 as dkd over, dkd, and so I end up with this thing. So on the top, and I'm just going to rearrange the terms a little bit just in terms of how they're usually written. So the nkn, I'll write it as n nk over d dk. Then over here, I'm going to get d dk plus n nk over d dk. Okay, so So I just found like the common factor right here. Put it this way. Notice I can now slash those things right there. And I get that my closed loop transfer function is, so put it right here. So in my numerator, I'm going to have n and k. Denominator is n and k plus ddk. Okay. So this right here, this is going to be my, really that closed loop polynomial. That's the most important. That one's going to be what determines the whole system behavior. So this is, I'll say it's the closed loop. This n and k plus ddk is going to be the closed loop characteristic polynomial. So really all those dynamics of settling time, rise time, percent overshoot, stability, all of that is going to be embedded in this n and k plus ddk. And so if we, so let's say if we set dt as a desired, let's say polynomial, closed loop polynomial. So basically, if dt is the polynomial that has the behavior that you want, then let's say then we can say the following, and we can write it this way. We can, like, our goal becomes to solve n and k plus d dk equal dt. So this dt becomes your, this is set by you. It's set by, this might be the polynomial that describes the percent overshoot and everything that you want. And then your goal then is going to be to solve this equation right here, denominator, make that equal to your desired polynomial. And again, and we're solving this with respect to nk and dk. So this becomes the big equation we have to solve. This one has a special name. It's known as the Diophantine equation. And by the way, I'll go back to where I originally wrote the title, just so we don't forget. So when we're talking about pole placement, I'll say via Diophantine equation. And really what we're doing is, this is all based around output feedback. So we're taking this output and bringing it back. And I'll say via Diophantine equation and output feedback. Yeah, there might be other ways to get the performance that we want, but here we're using output feedback, just as usual, taking our output and feeding it back in. So I'm using output feedback, and it led us to this huge, like, really important equation right here. So huge in terms of importance, not necessarily in terms of it's going to be a big, like, difficult equation. It may or may not. But again, our goal is going to be to find dk, nk, and dk so as to meet the specs determined by this dt. Right. So let's try this out right here with an example. See how that goes. Let's do a little example. And for example, let's say that my the plant G is given by the following. Let's say the G is going to be 4 over S plus 1, S plus 4. All right. And let's also say that the desired pole location for your performance specs and stability and all that. So your desired pole location is going to be the following. It's going to be S1 and 2. You want to make sure that they're all nice and stable. So let's having a -2. And for percent overshoot and all that, they want them at plus or minus J2. -2 plus or minus J2. And because this was an order 3 system, there's a third pole location that they're moving or they want to move over to S equal, just keep this simple, S equal -2. So these are the desired pole locations. So again, our goal is going to be to find a controller, find K of S, which again is equal to NK over DK to meet the specs above. Okay. So again, this might be, initially it might be like, well, okay, this is pretty bold. You're just giving us a plat. You're giving us these 3 arbitrary pole locations and saying, okay, you want to design a controller so as to, with that closed loop system. And again, I'm just going to have it up here for good measure, but you guys know what it looks like. We're using our classic negative unity feedback, so you don't have to redraw it. I'll just have it here as a reference. So for this, given this plant G, given we want to find this controller K, so that my overall dynamics have this as the main, as the poles. These are the overall closed loop poles. So in terms of solving this, we would say, all right, we just learned this new equation, that Diophantine equation. And so let's say, well, let's use that new equation, which seems to be geared at precisely that. And the new equation, the Diophantine equation. So here I wrote Diof equation. It says N NK plus D dk equal to dt, where again, this dt is that desired polynomial. It's going to be that desired polynomial. N and D are the numerator and denominator of the plant. NK and DK, numerator and denominator of my controller. All right. So first things first, these are the 2 things we're trying to find, NK and DK. And these 2 are given. This one we can, it's kind of given, and we can build. So real quick, by looking at what's given in the problem, what is N? What is that N of S right here? Yes, 4. Good. All right. So it's just the numerator of the plant. N is the numerator of the plant. Let's, you want to be thorough about it. It's N of S. In this case, it's just a constant, so it's just 4. And then D is going to be that denominator, right? So it's going to be this thing right here. That's going to be, so S plus 1, S plus 4. And we can multiply it out just to have it in a more complete or let's say easier than to do the math. So d, if we multiply it out, it's going to be, and you can confirm, but what I have here is s cubed plus 5s squared plus 4. S cubed. So you can just double check there that this this matches with that. So again, n is we figured it out. D we figured out. So that is fantastic. That's a good start, right? Now, next thing we need is this dt. So that's the desired polynomial. The desired polynomial. So this is the polynomial that captures the dynamics that we want. Here, we weren't necessarily told, hey, this is your desired polynomial. But could we build it off of that? This one right here? Yeah. So it's just 4. So n is the numerator of the plant, d is the denominator of the plant. So numerator of the plant is 4. Denominator of the plant is this one right here. And oh, and down here at the end, yeah, it's 4s. I thought you were asking me about this, but yeah, exactly right. So this is just going to be my denominator of the plant, and I just multiply times 3. All right, so then, but then yeah, we need the one on the right side. So dt is going to be the polynomial that captured the desired behavior. Here I was given the desired poles. So what we can do it is just sort of build our dt based on those desired poles. So if the desired poles are S1, S2, S3, my dt is going to be S minus S1, S minus S2, S minus S3. In this case, there was 3 of them, but there might be cases where I'm only given two desired polynomials, and that's, or 2 desired poles, and that's totally fine. I would get a system of order 2 then. Or if I just have the 1, I would just get a system of order 1. In this case, I was given 3 desired pole locations. So we know that the poles are what makes the denominator 0. So this is how I set it up. Essentially factored S minus S1, S minus S2, S minus S3. And so in this case, I would just do the math here. So this is going to be S minus -2 plus 2j times S minus -2 minus 2j. And the third one was just S minus 2. So that is my dt. There we go. All right. So S minus or S plus 2. Okay. So then we can just multiply all of these things together and we would get our polynomial. So again, just like we did up here, we want everything just in polynomial form. That's going to make things nice and straightforward. So if I do that, and you can, probably the easier way to do it would be to multiply these 2 together first and then multiply that by s plus 2. If you want to do that quick in your calculator, you may. I'll write over here what I have for my dt. So I have s cubed plus 6s squared plus 16s plus 16. All right. So now look, we've got our equation. We got n k equals ddk equals dt. We've got n, we've got d, and we've got dt. And so our goal is going to be to find nk and dk. So let's set it up. Nnk plus ddk equals dt. So I get 4 times nk plus ddk. So I'm going to get, oh, just kidding. Yeah, no, 4 nk, yes. And then plus d, which is this one, times dk. So I'm going to get s cubed plus 5s squared plus 4s times dk. And that's going to be equal to dt. S cubed plus 6s squared plus 16s plus 16. So n and k plus d dk equal dt. Again, this right here is my dt. This right here is d. This right here is n. And so that's my equation right there. Now, there's going to be several ways to solve this equation, but essentially our approach is going to be to try to match up the coefficients on the left with the ones on the right. So make sure that whatever is in front of my s cubed here matches what's in front of my s cubed here. Whatever's in front of my s squared here, so this would be a 6, matches whatever's in front of my s squared on the left. And so one way we could do it, I mean, this might not be the only way to do it, but notice the coefficient right here for s cubed is 1, right? Here I've got this s cubed. So I'm just saying, how about we take dk equal to 1, and then just build everything else into the nk. That's one way to do it. So I'll say one approach. Or one solution. Might not be the only solution, but you know, one solution. Let's take, or let's say set dk equal 1. Again, if I set dk equal to 1, then that takes care of all my s cubed terms. I would just need nk to be a term that captures everything else for s squared, s, and the constant term. So I can do that. And then nk, it would be a quadratic term because notice everything else would need to be built into the nk. So let's call this b2s squared plus b1s plus b0. And please let me know if yeah, if you need me to repeat this or if you're with me so far. So again, I took this as just perhaps the easiest thing mathematically that I could think of like, well, I've got 1s squared, 1s cubed. I've got this 1s cubed. I'll just take the dk equal 1, and that'll leave this term alone. And then everything else that I need to do to match coefficients, I'll build into my nk. And so this is how I set up my nk in order to do that. And I'll say equating coefficients. Equating coefficients, I get the following. So my k of s, so it's going to be nk over dk. But dk we said was equal to 1. I set it equal to 1. And equating coefficients, I find my D2, my D1, and my D0 for things to line up. And I got the following: 1/4 S squared plus 3S plus 4. So this would be your controller that if you put that controller in there for that negative unity feedback system, that's going to give you all of this up here. Like it's going to give you the closed loop poles exactly at those locations. And so hopefully you'd be very happy with that controller right there. Now, let me ask you, like, are you happy with the controller, or is there something about it that makes you uncomfortable or unhappy? Yes, Nick Graff. Let's see up here. So 3S. Yeah, so notice it does match up. So we need 16S right here altogether. And I've got four NK. So 4 times the 3S is 12. And then over here I've got 4 more. So that does work out. It's all good. Yes, Scott? Yeah. So that's kind of weird, right? Pretty much everything that we've seen so far, the denominator has a bigger order than the numerator. Right here, we did it for mathematical convenience, but we've got a denominator of 1, so basically a denominator of order 0, and a numerator of order 2. That seems to be very unusual and very, just not what we're used to. And there's a reason that it's not what we're used to. This thing right here is what's known as a non-proper transfer function. It's a non-proper transfer function. And when you've got a non-proper transfer function, it gives you all sorts of problems with causality, and you can't really implement that in practice. So a non-proper transfer function, again, it's going to be, I'll say, not useful in practice. Okay, so that's, and again, that's due to the fact that my numerator here has order 2, and my denominator was just that constant 1, so order 0. So the fact that the numerator had a higher order than denominator leads you to a non-proper transfer function. And again, that's going to give you problems with causality, not useful in practice. So that absolutely sucks because we did all that work and we went through that equation that we thought was beautifully set up. And over here, I'm like, okay, this seems to make the math all work out, and mathematically it's true, but it leads us to this kind of just useless, unhappy place. So what do you guys think? Should we just ditch what we did? Is there hope to this Diophantine equation? Is it a completely useless approach? What are your thoughts? So we just say F it and move on, just plug it into MATLAB and hope for the best. I mean, what does Hunter Baudet, what does your instinct tell you? Yeah, figure out how to go on the team because one possibility, like one possible solution. That solution doesn't work because I'm thinking that maybe potentially another one. Yeah. I like that approach, right? Like it's like the idea is like, oh, a host structure seemed to be pretty good. This equation seemed to be pretty well set up. And then it was right here when we built the equation, and it's like, how do we solve it mathematically? And we set it up this way. What Hunter's saying, could we not, yeah, put some constraints as to how we build the solution so that we end up with something that actually works. So indeed, what we're going to do is essentially set some guidelines to the Open-Team equation and set some guidelines to how to set up the solution for it as well. And that way we're not throwing away our whole approach. It's still going to be a really powerful approach. But just need some guidelines so we don't run into this situation right here. So let's explore that. So let's introduce then, so we don't run into those issues, some guidelines for Diophantine equation. And again, just as a reminder, yes, it's still the same equation, n and k plus d dk equal dt. And what we're trying to avoid is having the numerator have a greater order than the denominator. So the guidelines, the first thing is, first one is going to be G. So G, which is the plant. Sec here. I don't get why my computer, I guess everybody's, why it's so eager to like update all the time. Calm down, calm down. All right, so G, the plant, it needs to be strictly proper. Needs to be strictly proper. And what that means is that the denominator, the degree, basically degree of D needs to be greater than the degree of N. So if you just have proper without strictly, then it's greater or equal. But if it's strictly proper, the degree of the denominator needs to be greater than the degree of N. So if we're given a plant for which this is not true, then the whole thing won't work. So we need to start with a plant that's strictly proper for this equation to work. And our goal is to get a controller that is proper. So next up, what we're going to do is to work on dt. So I'll say, let's choose dt. So that the degree of dt, needs to be greater or equal than 2 times the degree of d minus 1. Again, if we don't have that, the whole thing won't work. So this is the degree of the plant, and the desired one needs to match this right here, which I think makes sense. I mean, if you think about it, this is the degree of the plant, and imagine if you've got a plant of order 10, and you've said your desired polynomial is like order 2. There's no way that you're going to have something that works with that little with that level of simplicity here. You need something more involved in your degree of dt. So for things to work, indeed, your degree of dt needs to be sufficiently high. And sometimes I'll make the note, sometimes you'll need to add extra poles. All right. Then And we'll get back to this issue of adding extra poles. But remember that if you've got, let's say, for example, someone tells you, I want this percent overshoot and I want this settling time. So you know that that corresponds to a couple of poles somewhere. But you do this and you realize, oh crap, I need it to be of order 3. Then you need to add an extra pole. Usually what you do is you put any extra poles far to the left, because the farther they are to the left, the less dominant they are. So I'll just add the note. Sometimes you need to add extra poles to DT. Um, and let's say, let's place additional poles far to the left. There we go. So all right. So that sets our DT. But then our big issue was with DK and NK. So for here, in terms of the order of DK and NK, we're going to choose the degree of DK as degree of DT minus degree of D. And then finally, let's choose degree of NK equal degree of DK. Okay. So if we do this every single time, K is going to be guaranteed to be proper, like the equation is going to work out, and our controller is going to be proper. The controller won't be strictly proper. The degree are going to match. The degree of the numerator and denominator are going to match, but it's going to be close enough. So again, we need to ensure that the plant meets it. Then we need a degree of the desired one that's high enough. And then we would set the degree of my controller this way, DK and NK this way. All right, so that's the guidelines to apply the equation. As long as we follow those guidelines, then that powerful equation should work for us. So let's get started. I'll give you guys a problem and see how that goes. So yeah, at least let's get started. And by the way, on Thursday, we'll just do a bunch of practice problems with this Diophantine equation. So kind of following the Tuesday more for theory, Thursday more for practice. But let's get started with a problem right now. So let's do an example. Let's say that we've got the classic situation. I'll just, again, draw it up here for reference. You don't have to redraw it all over again. But negative unity feedback situation right there with y and r plus minus. And so let's do one like this. So let's say that the plant g of s is 1 over s squared minus 2s plus 1. Okay, so that's your plant. And your desired closed loop poles, are the following. S1 and 2 are -1 and -2. And your goal is going to be to find the K of S. That does the trick for us. Okay. So how about you give it a shot? Like, let's say it's 8:50 or so. So I'll let you get started, and you can do it on your own, and then we'll check in about 5 minutes or so. If you're here in the classroom, feel free to check with your buddies who are nearby. Otherwise, if you're at home, you can always, type to your friends to see if they're on the same page. But I want you to get it started and see how that goes. Okay. So actually, with this first one, I'll check along with you guys right here. So I've got my Diophantine equation, n and k plus d dk equal dt. But in order to get it to work, we need to ensure that all those guidelines we just went over check out. So first thing is G strictly proper? Because if it's not, then the method won't work. We simply need to do something else. So we would go up here and look, okay, G, notice that the denominator here it has higher order than the numerator. So yep, G is strictly proper. So in that case, we are good. Next thing was degree of dt. Degree of dt needs to be greater or equal than 2 times degree of d minus 1. And in this case, d is this guy right here. So the degree of d for us is going to be equal to 2. Therefore, degree of dt needs to be greater or equal than 2 times 2 minus 1 than 3, right? Degree of dt needs to be greater or equal than 3. Okay. So let's build that dt. So notice that dt is going to be equal to so it's going to be, let's say, s minus 1, s minus 2. But then we need a third one, right? So we were given these two guys right here, s minus 1 and s minus 2, but we need a third pole. So I'll add an s minus 3, and then this is going to be an additional pole. So the ss minus 1, ss minus 2 are given to us up here. So this would be s plus 1, s plus 2. And then this pole we want pretty far to the left. So rule of thumb, we would put that about 10 times as far away as the next one. So here we've got this s plus 1 and this s plus 2. So if you want it far away enough that it doesn't affect you a whole lot, you would do it 10 times as far away as this one. So we would do s plus 20. Okay. Again, 20 because that's 10 times as far away as the 2. And then the dt, we would just multiply all these through. I have not done that algebra over here in my notes, so I'll let you do it, and you can dictate to me when you've got it. So, or if someone has a calculator and just wants to shout it out, please do. So it's going to be s cubed plus something s squared plus something s plus something else. Okay. So Nika, David tells me that it's s cubed plus 23s squared plus 62s plus 40. Thank you, Nika. Appreciate it. Great. So that becomes our dt right there. Fantastic. So in this case, we're set with strictly proper. We're set with our degree of d, and we actually have the dt that's going to go right here. We know that going back up here, this was our n, this was our d, and the last thing is the degree of dk and degree of nk. So we know degree of dk is equal to degree of dt minus degree of d. So that's going to be degree of dt we said was 3. The degree of d is 2. So therefore this is going to be equal to 1. And then my degree of nk always matches that. So degree of nk is always equal to degree of dk, which is equal to 1 as well. Okay. So one way is we know they're going to be both of degree 1. So let's let nk equals b1s plus b0. So it's just an arbitrary polynomial of order 1, and then dk, let's call it a1s plus a0. Okay, so at this point, like the last things we'll need to do is to use the equation to find b1, b0, a1, a0 with the nk and dk from above and the d2 from above. So let's do that. So now we're free to apply the Diophantine equation. Now we can apply the Diophantine equation. Again, that's n and k plus d dk equal dt. We said our n was equal to 1, and our nk was b1s plus b0. Our d was the denominator of the plant, so it was s squared minus 2s plus 1. And then, so that's the dk. Oh, I'm sorry, that's d. And then the dk we said was a1s plus a0. And then on the right, we would have our dt, which was s cubed plus 23s squared plus 62s plus 40. And now what we're going to do is multiply and equate to coefficients. So from this point, we multiply through, then we're going to group, and we're going to equate coefficients. Okay, so just a little bit of algebra. Notice that here for this first one, just multiplying by 1, so that states as b1s plus b0. Nothing too fancy there. Then over here, it's a1s times this whole thing. So I'm going to get a1 s cubed minus 2 a1 s squared plus a1s. Okay, so that's taking that and multiplying by that. And then let's take this and multiply by a0. So I get plus a0 s squared minus 2 a0 s plus 1 times a0. And this again is going to be equal to the stuff on the right, s cubed plus 23s squared plus 62s plus 40. Next step is going to be to group terms. So on the left, I've got one term only with s cubed, so I'm going to get a1 s cubed. And then for s squared, let's see, s squared shows up a couple of times. So I'm going to get right here a0 minus 2a1 s squared on the left. Then the term with s, that one shows up 3 times. So I'm going to get b1 plus a1 minus 2a0 s. And then finally, the constant terms are just going to be b0 and a0. By the way, if you catch a mistake, something that I missed, let me know. But I think that's correct. And again, we equate that to the same thing. All right, so now we are ready to equate coefficient by coefficient. So notice for the s cubed terms, from the s cubed terms, I get that a1, which is my coefficient here, has to match up with a 1. So a1 equal to 1 right away. Okay. So if a1 equal to 1, from the s squared coefficients, I know that a0 minus 2a1, that needs to be equal to 23. But from before, I know that a1 is equal to 1. So this is equal to 1. Then a0 is equal to 25. Okay. Then from this term right here, s to the 1, I get that my b1 plus a1 minus 2a0 is equal to 62. Now we said that a1 was equal to 1 and a0 was equal to 25. Okay. So from there, I get what? b1 equal 86, is that right? Oh, yeah. You're right. I've been seeing that too. All right. So 2 times 50 is, so this would take you to 112. So 111, right? Thank you. Yeah, so thanks for that. 111. And then finally from my S0 term right here, S0, I get B naught plus A naught equal 40. Okay. And I know my A naught is equal to 25. So B naught is 40 minus 25, which is equal to 15. Okay. So at this point, we've got all our terms. From there, we know that the K of S, which is B1S plus B0 over N1S plus A1S plus A0. So it's going to be 111S plus 15. And then my denominator, A1S, so just S. Oops, ugly S. Then S plus 25. Okay. And that becomes the transfer function then that you can use to get that desired performance. So then that would conclude our problem. All right, folks. So questions as to this procedure. Notice that it might seem like a lot of algebra, but it's a really powerful procedure in that it's, from here, we essentially can design a controller so as to get us any output at all or any type of performance that we want for whatever plant. So I mean that's a lot of power to this procedure. I'll tell you, it does have some downsides. As we know, the plant needs to be strictly proper, which it isn't always, and it's also pretty susceptible to parameter variations. So if you've got a plant where going back here, where like if you've got a plant that's given to you like this, and it turns out that in reality, this wasn't a 2, that it was actually 1.9, and maybe this wasn't a 1, maybe it was 1.1 or something. Those little variations will mess you up a lot. So that's one of the, it's a powerful, but also slightly finicky method from that point of view. So it does have that disadvantage. Okay. So folks, this is where I wanted to get to in terms of the theory. On Thursday, it's going to be all practice, all the open team practice. So I'll bring you, I might even post on Canvas just a few problems, and we'll just have an opportunity to work here in groups and solve them so you get comfortable with that. All right, so let's leave it right here. And yeah, see you all Thursday.